In this video, we will continue talking about Newton-Raphson method. We will focus on how to implement this method in MATLAB to find the root of nonlinear equations. Let's see this example 2. Consider the function fx, which is equal to x squared minus 2, and start with the initial guess x0 equal to 2, and assume that the two epsilon constants are 1e negative 5, and the maximum number of iterations n is equal to 100. The first question asks you to write all the codes in the main file, and the second question asks you to write the codes in the main file and a separate file, separate function file, which is called Newton-Raphson.m. For the iteration, you can use either while loop or you can use for loop, because right now we have a maximum number of iterations n, which is equal to 100. So this method, if it converges, it usually converges very fast. So if it doesn't converge within 100 iterations, it's very likely that it will never converge. So 100 is a reasonable number for the maximum of iterations. So let's see how to do problem 1. So we need to write all the files, all the codes in the main file. So we need to create a new script. Clear all, close all. If you want to see more digits, you can format long. And let's save this as main file. All right. Then we need to define the function, which is function f, because we need to write all the codes in the main file, so we should not create a separate function file for f, right? So we need to use the @ symbol to define this function within the main file. So x squared minus 2. So let's use the dot operation here because x may be a vector. Then for Newton-Raphson method, not only you need to define the function, also you need to define the derivative of the function. So let's define df, which is 2 times x, right? Then we have those constants, the initial guess x, which is 2, and the maximum number of iteration, which is 100, and the epsilon step, which is 1e negative 5, negative 5. Also epsilon abs, which is 1e negative 5. Okay. Then we can start the loop, which is a for loop, because we know that the maximum number of iterations we want to do is n. When we start the iteration, we need to find the next approximation based on the x value we have right now. So x will be update based on the old value of x. According to the formula, it's equal to x minus fx over the derivative dfx, right? So this is the formula to get x update. After you get x update, remember that there are 3 different scenarios. The first one is it converges, then both condition A and condition B are satisfied. So condition A is that the step, which is the distance between x update and x, is sufficiently small. So it's less than epsilon step. So abs x update minus x less than epsilon abs, epsilon step, sorry. And the second condition is satisfied, and condition B is that the absolute value of f x update is less than epsilon abs. So abs fx update less than epsilon abs. Here should be a bracket. Okay, so if condition A and condition B are both satisfied, then we find the root, right, which is x update. Then we can stop the iteration by using break. So the next scenario is that we have this division by 0 problem. However, we don't have to explicitly consider this scenario. The scenario 2 can be included in the scenario 3, which is when we reaches the maximum number of iteration n, the process still doesn't converge. Because when you have a division by 0 problem, you will never, the process will never converge, right? So it's included in the third scenario. And also, when you have a division by 0 problem, MATLAB will now send you an error. It will continue the numerical process. For example, you have 2 divided by 1 minus 1. It will give you a large number, INF, but it will not terminate the program by giving you an error message. INF in MATLAB is a very large number. Basically, when your result is very large, when it's larger than a certain constant, MATLAB will stop showing you the digits, and instead it will show you as INF. So INF is a number in MATLAB. Okay, so because if you have the division by 0 problem, MATLAB will continue running, so we don't have to consider this scenario as explicitly. It will be included in the third scenario, which is when I reaches n, it will send a error message to the user, says that Newton-Raphson method does not converge. Okay, then you need to change your initial guess or change to another method. So this is the 3 different scenarios. So numerically, it becomes 2 different scenarios. Okay. So for each iteration, after you get x update based on the value of x, the next time when you start the next iteration, the x update become x, right? So you need to update this x value by assigning the value of update, x update, to the variable x, right? So then we can end this for loop. All right, so let's run this to see what happens. Then you can find the root. Okay, so which is very close to the square root of 2. Okay, so this main file works very well. And then before we talk about problem 2, let me show you how to visualize this iteration process, because sometimes it converges, sometimes it doesn't converge. If it doesn't converge, we want to know what happens, right? So it's better to be able to visualize this process. Okay, so it's very similar to the to what we did previously. We need to plot this function around the area around this initial guess, right? In the area around this initial guess. So assume that we have a vector xx, which is some x coordinates close to the point x equal to 2, right? So we plot for x minus 2, from x minus 2 to x plus 2 with the interval 0.01. Then the yy will be f(x)(x). Then we plot x(x)(y)(y) by using the blue line. Then we hold on, because later we will plot something else on the same figure. You can also add a grid on. Okay, so for each iteration, let me show you here. So for example, if the function looks like this, right? So this will be the root, and we start from a initial guess, which is here. So this is x0, and if we draw a vertical line which intersects the function at this point, then we draw a tangent line, right, which intersects the x-axis at x1, right? So if you want to visualize this process, we want to draw this line, right, this vertical line, and also this tangent line here. So how to draw this vertical line? So you can see the coordinate of this point is x0, 0, right? And the coordinate of this point is x0, fx0, right? And the coordinate of this point is x1, 0. So with those coordinates, we can plot the straight line by connecting two of the points. Right, so we can define the x-coordinate of the first 2 points as xp, which is a 2-element vector. So you can see here it's x, because this plot is for x0 and x1, but it can be xi to xi plus 1, right? So it should be the x-coordinate for the 2 points is x0, xi, and xi, right? So it should be x, and the y-coordinate for the 2 points is 0 in fxi, right? So it should be 0 and fx. Then we can plot xp, yp by using right line for the vertical line, and then hold on. Then we need to draw the tangent line. So the x-coordinate for the tangent line, which is x1 and x0, right? So which is x update and x. So xp2 is equal to x update and x, right? So yp2, so you can see here the y-coordinate is 0 in fx. So it should be 0 in fx. Then we plot xp2, yp2, use green line for the tangent line, and then we can hold on. Then we can run. So this is the order plots. So you can see we can zoom in a little bit by we can plot x minus 1 to x plus 1, and then we can, after each iteration, we can pause. Okay, so when you pause, you need to press the enter key to continue. This will be the first iteration, and then you see this is the second iteration, and then you can see the third. Okay, so because it converges so fast and very quickly, it's extremely close to the root, so the plot was not very clear. But you get the idea about how to plot. Okay. So let's see the next question. Write the codes in the main file and also a separate function file, newton-raphson.m. Okay, So assume this is the main file. So after we define this f, derivative of f, and those constants, initial guess x, maximum number of iteration n, and 2 epsilon constants, we can call a function to get the root, right? So root equal to Newton Raphson. The input parameter is f df x n and 2 epsilons. So we can create a function file, which is function root equal to Newton Raphson f df x n epsilon step epsilon abs. So we can save this as Newton Raphson.m. Okay, and then we can copy paste this part into the function file and then save it. Okay, so we can run this file. Okay, so the root will be very close to the square root of 2. Okay, so this works. And the next, I will show you how to in this function file, we write the iteration by using for loop, and alternatively, you can also use while loop to do that. So I will show you how to use while loop. All right, so for loop, so we remove this for, can change to while loop. So while, right, so there are 2 conditions for the halting condition. One, condition A and condition B is satisfied, we need to halt, right? So when you use while loop, it should be the opposite of this condition, and if it is satisfied, then we continue, right? So it'd be the opposite of A or the opposite of B. If this is satisfied, then we continue, right? So this is the condition we need to write for the while loop. So remember that condition A is that the step, the distance between n plus 1 and xn is sufficiently small, less than epsilon step, right? So A opposite should be the absolute value of xn plus 1 minus xn larger than or equal to epsilon step, right? So the condition B is that the absolute value of f xn plus 1 is sufficiently small. It's less than epsilon abs. So B opposite will be the absolute value of f xn plus 1 larger than or equal to epsilon abs. Okay, so let's put this condition as the condition for the while loop. So first it should be abs x update minus x larger than or equal to epsilon step, or abs fx update larger than or equal to epsilon abs. All right. Okay. There is a bracket. So this is the condition for the while loop. If this is satisfied, then we find x update based on x. Then we can do the plot. And so the if condition should be changed, right? So this is already taken care of. So the only scenario is that I is equal to the number of n. So we need to set up a counter I, which counts like how many iterations we have done, right? So I initially is 0, and after each update, after each iteration, I become I plus 1. Okay, so then we can judge if I is equal to n. If that happens, we get an error, and you can stop the while loop. You can break. Actually, this is an error, so it already breaks, I think. So you can change this to display and break. And then you update the value of x by assigning the value of x update to the variable x, right? So in the end, the root, you can write outside the while loop, so the root will be x update, right? So this will be the using the while loop. Oh, so here you can see x is from the user input, right? So we get the value of x from the user. However, x update appears in the condition for the while loop, but there is no initial value for this x update. So we need to initialize x update. When we initialize this variable, we need to be very careful because we want to make sure the while loop is triggered. So we will we can go into the while loop. So x update minus x should be larger than or equal to this epsilon step. So we can assume x update equal to x plus epsilon step plus 100, right? So this is to make sure the while loop will be triggered. And let's try if this works. Okay. Okay, so it works. All right, so this is how to write down the Newton-Raphson function by using both while loop and for loop. So let me show you the quiz question. So this quiz problem is the problem 6.27 on the textbook page 181. Use the Newton-Raphson method to find the root of a nonlinear equation f(x), which is e to the power of negative 0.5 times x, and then times 4 minus x, and then minus 2. You need to use you need to use 3 different initial guesses. The first one is 2, the second one is 6, the last one is 8. And you need to write the codes in the main file and a separate function file, newtonraphson.m. So you can use either while loop or the for loop for the iteration, and you need to explain your results. For some initial guesses, Newton-Raphson method does not converge, so you need to show us why it doesn't converge. So it's better that if your code can visualize the iteration process, just as I showed you in the example problem. Okay, so this is the class for Newton-Raphson method. In the next class, we will talk about another open method, which is called the secant method. It's very similar to Newton-Raphson. It's in the textbook, chapter 6.